Welcome, welcome, welcome. Hello, everybody. I hope you can hear my voice. And welcome to our very first AI in Telecom Meetup being done via a live stream. And it's kind of an exciting thing to do it this way. Do me a favor and jump into the chat. Oh, I see one person that's jumped into the chat and is saying hello to me. I really appreciate that. I want to make sure that everything is working. I will be the first to admit I am new to the live stream phenomenon. I've watched a number of things on Twitch, but I have never actually done a live stream. Oh yes, I got a couple of people who are on there now. Fantastic, fantastic. Well, welcome everybody. If you have joined over the last few minutes, you've been listening to a very interesting set of music. It was from a group of people called Botnik, and I've mentioned Botnik before in the meetup. And Botnik is a group of people out of, I want to say, the West Coast. They're a comedy group, but they do a lot of AI-generated things. They have AI-generated fan fiction. They have an AI-generated predictive keyboard. And this was a CD, or a CD that they released earlier this year called The Songularity, right? So kind of a play on singularity. The Songularity. And the Songularity is really just a compilation of music that they've put together that's all AI generated. And I don't know exactly how much is AI generated. The impression I get is at least the words are, the music itself is. I don't know if the singing is. I don't think it is. But I find it quite interesting. So during this era of Coronapocalypse, that's what I saw on Twitter, and that's the term I like the most. But during this era of Coronapocalypse, we have at least one thing that we can appreciate. That is AI-generated music. So again, welcome everybody that's on the meetup. What we're going to talk about today is quantum computing and AI. And this is a topic that I picked, okay, can you tell us the name of the artist again? The artist's name is Botnik, B-O-T-N-I-K. Put it in the chat as well. And it's kind of a play on the word beatnik, right? So beatnik is an old term, if you're not familiar with the term, it's a term of kind of the counterculture, that kind of the poets of the 50s. If you've ever heard the term of the beat generation, that's kind of where this comes from. And so they're kind of making a play on that, and they're calling it Botnik. And they do have some interesting stuff that's on their website. Like I said, they have a really interesting predictive keyboard that they do, and they're currently in a series on their blog, their email newsletter of it's Harry Potter and the Little Prince is, I think, the name of it, but it's basically Harry Potter fan fiction that's AI generated. And what they do is they use an LSTM, a long-term, short-term memory RNN model, and they generate a set of really randomly generated sentences based off of the writings of J.K. Rowling's. And then they have a human being go in there and convert that to basically clean up the grammar. Because the models don't do a perfect job with that. And they don't typically do punctuation, and they don't typically get, sometimes you'll have these run-on sentences that are kind of crazy. But what they've done is they've done that, and then they'll clean it up, and then they have this AI-generated fan fiction. And it's usually pretty funny. It's not awesome, but it's usually pretty funny, and it's worth checking out. There are other sites that do AI-generated music, and those are interesting. And I was looking at those a little bit. as some kind of interesting intro music to play during this, but I decided to go ahead and go with the Singularity. And if you had a chance to listen to it, it is on iTunes, so you can find it. I just find it hilarious. They have a song that I think is they used to, they trained it based off of Smith's songs called Bored with This Dyer to Get Ripped. And it is just really funny. And then another one called Soviet Nights that I think is trained using Beach Boys songs. So it's quite interesting. It's quite interesting. So what do we want to talk about today? So what I wanted to talk about today was quantum computing and AI. And really where this comes from is I looked at a Gartner hype cycle on AI about 2 months ago, and I wanted to come up with topics for the next couple of meetups, and I just walked around my office and said, which of these topics are interesting to you? And that was still before the corona apocalypse has happened, and we're all working from home, as you can see based off of my camera. I am currently in my home office, aka bedroom, and so walking around and asking people their opinion is probably not going to happen for, if you listen to the CDC yesterday, the next 8 weeks. But I walked around my office and I said, what is a topic that's interesting to you? And so last month we did AutoML, because that was one of the things that was kind of interest to people in the office. And now quantum computing was the topic that came up. And so I wanted to talk a little bit about quantum computing. And so a little bit of background. This is sponsored by Word Solutions. We typically are in the same room, and we typically have pizza, so I hope you're enjoying some virtual pizza at least. We are a technology training partner for the world's best networks. We would have been featured at Mobile World Congress had Mobile World Congress happened. We would have been featured at the CCA Mobile Carrier Show coming up later this month. Again, if it would happen. Our hope is that in the September-October timeframe, we are actually featured at Mobile World Congress America in LA. And that will happen given the kind of conclusion of Corona Apocalypse. Starting in April, we're going to be re-kicking off our complimentary web series, and we're going to be doing a building an AI-based application. And so if you weren't able to attend our building an AI-based application meetup a few months ago, or you're just interested in the topic, or you want to communicate that to your friends and neighbors, feel free to share that. The link is there on the slide, and we're going to kick that off in April. So what do we want to talk about today? What we want to talk about today is really what is quantum computing? And this is going to be a very, very high level. That's a good point. Can I post the link to the meetup? Beverly, if you can post the link into the chat, that would be fantastic, because I think you'll be able to find it quicker than me. So this is going to be a very high level discussion of quantum computing, super high level. I've got to have, full disclosure, my wife has a physics degree. She also has a chemistry degree. I have computer science and math. We met in calculus class, so it was a very romantic story. She understands physics a lot better than I do. As a matter of fact, the only physics class I took when I was in college was a descriptive physics class, a physics for non-science majors. And what we did is we spent the entire semester talking about how does Snoopy get off a frozen lake? And the answer is he throws his collar, and you have the equal and opposite motion. So that's it. That's my significant understanding of physics. But we're going to talk a little bit about quantum computing on a very, very high level. We're going to talk a little bit about the relationship between quantum computing and AI. And then lastly, what I'd like to do is I'd like to talk about the state of quantum computing. No, Beverly, not the link to the Meetup, the link to the complimentary webinar series. Okay, so that being said, let's go ahead and jump into this. So there are a number of references, and I will put the references in the chat as we go through so that you can have them. I am very heavily borrowing information from a lot of people, but this is the predominant set. And as a matter of fact, let me go ahead and grab a couple of those things now and put that into the chat. All right. Oh, thank you, Beverly. All right, so let's get started. What is quantum computing? Now, here's a definition that is in one of the pages of one of the articles that are on our the list that I've sent you, or I will send you, is quantum computing. It's a type of non-classical computing. It operates on quantum states of subatomic particles. These represent information as elements denoted as quantum bits or qubits. And this qubits is really the key to what we're going to talk about today. So a classical computer, it uses bits that are binary in nature. So it's either a 0 or a 1. A quantum computing uses something called a qubit. This is its fundamental bit. And here's the big difference. This qubit can be both a 0 and a 1 until it's read. And that's what really makes this very interesting. Because of these properties, we can also have qubits linked to other qubits. You can have a relationship that is built between these. And this is called entanglement. And we'll talk a little bit about entanglement in a second. So what quantum algorithms do is they're trying to do some type of manipulation of these bits based off of these quantum entanglements. And then we're trying to read these solutions. Okay? So this is a very high-level definition. But really the key thing is that qubit concept and how we're doing things different than classical computers. So what is a qubit? Well, a qubit is, and actually, a qubit is a superposition of two states that's denoted by a vector. And that vector is representing the probability that this is a 0 and the probability that this is a 1. And it's really this combination of both the ability to be a 0 and a 1 that becomes important. So today when we talk about how many bits a processor can support, in the futures we're starting to talk about quantum computing, it will be more of the number of qubits that you'll be able to support. And that'll be that metric that we're wanting to look at. How many qubits does this processor support? Now, there's a couple of key pieces of information that we need to take a look at with respect to this. The first is something called a superposition. And what a superposition is it's the probability that a state is either a 0 or a 1. A qubit is either a 0 or a 1. Now, again, based off this probability, it could be both a 0 and a 1. So it's the superposition that's allowing a single qubit to basically represent multiple pieces of information. Now, one of the things to keep in mind is where we are within the technology at this point. We are dealing with things at kind of this bit level. And if you've never had the opportunity to do things like assembly language programming, and when I was in college working on my computer science degree back in the 1900s, we did have to take an assembly class. We did have to take a class where we were having to look at things on that bit by bit, register by register level. And that's what I want us to think about as we're thinking about quantum computing today. Don't think about the laptop that you've got sitting in front of you. Don't think about giving an instruction set to an Intel processor. We're not there yet. Where we're at is we're at a, how do I manipulate these registers, these qubits? How do I create some type of relationship between them to solve a specific type of problem? Similar to an assembly language type of thing. So superposition is saying a given qubit, what's its probability of being a 0 or a 1? The next keyword is something, or key term, is called entanglement. Now, entanglement is a phenomenon where two particles, two qubits, so just as was mentioned in the chat, it started out in computing, classical computers started out as electronics at a gate level. And you'll see this pop up in quantum computing as well, is having a gate type programming. A question comes up, is there any good videos or websites that can help visualizing qubit states? I haven't seen any of those. There are some good websites, I'll talk about them in a little bit, where you can actually do some very basic programming. There's a couple of different sites that have quantum computers and you can do some very basic analysis of them. So entanglement. So entanglement is a very interesting property, and it's very important as we start to think about this low-level programming that we're trying to do. Once two qubits have become entangled, whatever their outcome, whatever their state is, persists. So in other words, what I can do is I can say, I want these two bits, these two qubits, to be the same value. And then what I can do is I can have some other set of operations here and some other set of operations here. And those additional sets of operations will be on this consistent data. It's like almost setting two variables equal to one another and then using those two variables in different formulas. And when one of those things change, the other one changes. So as the description I have up here on the right, once a pair or a group of particles, qubits, occupy the same state space, they are consistent. Now, one of the things that's interesting about qubits or this entanglement, and we're not going to get into this today at all, is the fact that entanglement could be persistent across very long distances. And so this is one of the things that people are looking at in just the communication field. If I can take two particles and I can entangle them, and I can separate those particles by a long distance, when I change one, I change the other. So in essence, could potentially be kind of the nucleus of a long-term communication. A long-distance communication, I should say. So how does this help? And this is really where I think it's quite interesting within what we're trying to look at. How does quantum computing affect speed? So on the left, I have a classical view of computing. And so as you can see, if I need to do something where I'm using an 8-bit register, what I have to do is I have to look at each of the possible values independently. So in other words, how many times do I have to go through this operation? Well, in this example, I would have to go through this 255 times. Because of this superposition, if I have an 8-qubit register, that one 8-qubit register is actually representing all of those possible outcomes. So in other words, with one 8-qubit register, I'm able to represent all 256 different possible outcomes. So if we're dealing with certain types of problems, this very significantly speeds up that outcome. Some of the examples I've seen are things like graph coloring problems, where I can basically set up these registers and try to optimize how everything can be set up so that I don't have adjacent graphs, adjacent nodes with the same color. So it's really this qubit trying to represent these multiple states simultaneously that's speeding up our process. And as you can imagine, not every system is going to allow for that to be of any value, right? So it depends on the problem that you're trying to solve. There's a big fear in the cybersecurity space with quantum computing because a lot of the encryption is done using basically using this assumption that how do I want to phrase this? It's using this assumption that a classical computer will take too long to break the encryption, right? So if I can encrypt my data and it takes you 1,000 years to decrypt it, it's secure because in 1,000 years, I'm not going to care. But what if I'm using quantum computing and it's going to be done in a much shorter amount of time? Now, this could be an issue. Okay, so one more background slide. I'm glad you feel that you're in the right place if most of the stuff is going over your head. I think that's great. Okay, so all of that said and done, there are 3 basic types of quantum computers, and this is where I think it's really important for us to understand the relationship between quantum computers and artificial intelligence. In the most generic sense, what we have is something called a universal quantum computer. Now, you can think of this universal quantum computer as being the ability to take the classic computing and extending it to the quantum space. Okay, so I had a question to repeat the encryption comment again. So let me do this. Let me do it this way. So one of the things within quantum computing and encryption is we're assuming that it's going to take a very long time to decode information. So the way a typical encryption system is I've got data. I'm going to apply some form of key to that data, and then I'm going to have my encrypted data. How do I get my data back? Depending on the nature of the system, what I may do is I may apply that same key, and then I get my original data back. So it's this key that's important. And the fundamental assumption in our encryption systems that we have today is our fundamental assumption is the amount of time it takes to determine this key is too long to be practical. So if we're using an algorithm like 128-bit or a 256-bit encryption key, which is very common that we use today, then for me to go through every possible combination, it would just take too long in our classical computers today. But what if I were able to do that not as individual iterations, but what if I were able to do that in a much faster amount of time with these qubits? So if I had a 128 qubit register, it would be one operation to try every combination. Right, so if we do some simple math, let me grab my calculator. We do some simple math and we say 2 to the 128, that's 3.4 times 10 to the 38th power. And if I do the same thing with 2 to the 256, that's 1.16 times 10 to the 77th power. So that's the reason that people are interested in quantum computing with respect to encryption. Because if I'm able to go from 3.4 times 10 to the 38th power to 1 or 2 operations, then that would greatly change the way we need to do our encryption. But what I want you to see, the reason I'm using that as an example, let me go back here for a second. The reason I'm using that as an example is because that's a specific type of problem, and quantum computing is helping that specific type of problem. Hold that thought for a second. We'll get to AI. So universal quantum computing is saying that we're going to basically create a really fast computer that's similar to what we have today. So in other words, all problems that we're able to solve today, we could solve just better in the quantum computing space. So in other words, you have general application. The second thing we have is something called quantum simulations. In quantum simulations, we're exploring specific problems in quantum physics that are beyond the capacity of classical systems. So in other words, what we're trying to do here is we're trying to find, the origin of the universe type of things. We're trying to solve problems that our classical computers haven't been able to do a good job of solving. But again, what we've done is we've shrunk our space of problems that we're able to address. Lastly, we have something called quantum annealing. And you'll notice how quantum annealing is the smallest portion of our 3 types of quantum computers, right? So universal is everything. Quantum simulation is a small subset. Quantum annealing, smaller still. And what quantum annealing is trying to do is it's trying to solve specific optimization problems. Specifically, it's trying to solve problems that are NP hard and NP hard problems. The reason they're so difficult to solve is because the solutions become exponential in complexity. And so this is where you start to see things like the graph coloring problems, or you start to see things like the traveling salesman problems. When my number of options starts to go up, the complexity also goes up. And what these quantum annealing systems are good at is trying to do optimization type problems. Okay, so universal quantum, that's really kind of utopia. That's the goal that we would like to get towards. Quantum simulations are really focusing on kind of these quantum physics related problems. And then quantum annealing is really just trying to solve even a smaller subset of kind of these optimization type problems. So that's a little bit on quantum computing. And there's a lot to it. I found so many articles, so many books, so many tutorials, and it is just amazing how much stuff there is out there. But we're still very, very early in this space. Yes, the rise of Skynet is inevitable. Nice. Love it. So, since our focus is really on quantum, or is on AI, right? We're the AI and telecom meetup. What is the relationship between quantum computing and AI? And this is really a little bit more of a harder thing. So if we go back to our AI and automation lifecycle, what we can see is that we have data that we need, and we all know about this. We want the ability to create a model. This is that training phase. And then we have this deployment phase, and this is really where we're doing the inference. And then we have some type of automation, some type of action that we're trying to take. The real computationally complex part is here. This is where we see a lot of GPUs being used. This is where we start to see TPUs used to do this training. Now, once we've trained a model, the actual inference, the using the model is much, much easier to do. And so when we start to think about using quantum computing, this is the place we need to think about with respect to AI. It's not really going to be the data gathering space. It's not really even going to be the inference space or the action space over here on the right. It's really going to be how we train this model. And what we're trying to do is we're trying to find a function that very well represents this model creation. Right? This very well represents this data. So how will quantum computing help? Well, universal quantum would help. Universal quantum would be great. It would solve a lot of our problems, but it's really not available today. We're still too early with that. There's certain people that are trying to do some things, but the number of registers you have are just so small. There's really not a lot going on. And I'll talk a little bit more about that in a couple of minutes. Quantum simulations, it's really solving the wrong type of problem. And then lastly, these quantum annealing, again, is solving a different type of problem. And so we're really more down in this space here today. And what we need is we need to wait for this to become more generally available. And we're just not quite there yet. Yeah, training is critical. Training is critical. And if we can speed that up, we've solved an awful lot of problems. Now, another way that we can look at this is, and this comes out of an article from Hacker Noon, and this was a pretty good article as well. I want to put that into the stream. But we can think of three different, a two-dimensional space. In the upper left-hand corner, what we're doing is we're looking at classical types of data. We're looking at classical types of data, a classical type of data, and a classical type of algorithm. This is when we think of AI, this is today. Because our data is just normal data. It's not focused on any type of quantum information. And we're trying to solve it using a solution technique of today. Cool. Where we want to get to is where we have more of this classical data, but we're able to use quantum algorithms to solve it. This is really the goal of our traditional artificial intelligence, our traditional machine learning. When we start looking at some of these quantum simulations, what we're trying to do is we're trying to take quantum data and solve it using some classical algorithms. Actually, it's probably this quantum simulations more here. But our goal is to really start using this classical data with these quantum algorithms. And again, like I've said, we're not quite there yet. So we talked a little bit about quantum computing. And we've talked a little bit about the relationship between quantum computing and AI. Let me pause for a second. Any other questions, comments from anybody that's out there in the live stream? Making sense? Give me some type of feedback if you would. When you talk about quantum computing, is it primarily more related to hardware? So yes, so when we talk about quantum computing, it is hardware related. There is hardware that's needing to be developed. And we'll talk a little bit about some of the kind of the state of that here in a second. Probably one of the biggest ones that at least I see a lot of stuff about is a company called Dwave, and another company, which you've probably heard of, called IBM. And Dwave and IBM are building these quantum computers, but right now the number of qubits are fairly low. So yes, it's really two things that I want you to take away from this. One is we do need this hardware, but two, it's the algorithms that can use this hardware. And both of those, I think, are critical. The hardware, if we don't have the hardware, the algorithms doesn't do us any good. A number of years ago, HPE was doing a lot of stuff related to something called the machine. And that was kind of their new approach to classical computing, where instead of having CPUs as the central piece and adding more memory, it was really making memory the central piece and adding more compute. I don't know that they've done a whole lot with it in the last couple of years. It was kind of their research project a few years ago. But to me, the big problem there was they had to design hardware and then they had to design software to support it. Now Python, there are some extensions, some libraries to Python that's specifically dealing with quantum computing. And you can, and so in some of these examples, if you go to D-Wave's website or you go to IBM's website, in both of those cases, what they have is they have simple Jupyter notebooks that you can set up that actually set up these basic quantum computing algorithms to run through. But again, they're fairly simple. So I used the analogy earlier of programming using assembly language. Well, that's a good analogy, but it's not really assembly language, but it is fairly low level. It would be using something like Python. All right, excellent. Good. Good questions, good discussion. So where are we today? So currently, we have two basic types of system, and we've talked a little bit about this. We have this this quantum annealing system, and this is really focusing on certain types of optimization problems. And then we have gate-based systems, and these gate-based systems are really trying to be more towards that universal quantum computing. And you can see there's a number of different quantum libraries that people have written, Ocean being one, different algorithms, different solvers, and there's even, as we've already said, an assembly language, a QMASM, quantum machine assembly language is what I would assume it stands for. On the gate-based systems, this is where we're trying to have more of those generic algorithms. So there are quantum libraries that are being developed. There are quantum algorithms that have been developed, quantum circuits, being able to control the noise, as well as their own assembly languages that have been developed. So it really feels like the 1950s and 1960s all over again, where we're trying to develop a very rudimentary circuit, and then we're trying to come up with systems of utilizing that circuit. And at the time in the 50s and 60s, especially the early 60s, we were dealing with assembly language before Fortran became kind of a commonplace. And really, if you've ever had the luxury of programming in Fortran is to me, Fortran feels like assembly language with a little bit of extra packaging. I wasn't a fan of Fortran. Two companies, in my opinion, kind of stand out. They seem to have the most in this in quantum computing, and that is D-Wave and IBM. Both D-Wave and IBM do have websites. You can go to their websites. They do have quantum as a service capabilities. You can program basic things using them. And it's amazing how fast some of those things are. And they do show you kind of that speed. Today, probably the biggest thing that's slowing you down if you are using one of their algorithms is just it's a shared system. So you have to wait your turn. And then once you wait your turn, you get the quantum computer and it does whatever it is you're wanting to do fairly quickly. So let me show you a website. This is kind of where I want to end our time together, is just as an interesting web page that has a scorecard of where people are at in developing this stuff. So let me post this in the chat. So this is a website that is just giving a qubit count. So this is really trying to show how big these systems have gotten. They're also showing things like the type of technology. When you see things like a gate system, really the goal is to get to this more towards that universal quantum computing. Yeah, and just as what was said in the chat, the time sharing is very, very similar to like a mainframe. Very, very similar. So you look at some of the, Intel, Google, IBM, they're in this double-digit number of qubits. Rigetti is at 32, trying to get into the 128. We scroll down a little bit more, and there's a long list here. We start getting into these quantum simulators, and in the quantum simulator space, there's a few that have 50-ish qubits. And then we start getting into the annealing type. And that's where they're starting to see things like 2048. And this is really where the problem is today, is where we're making the most advancements is in an area that doesn't help us as much in the machine learning space. Someone just put in the chat a nice article on what is quantum computing, and there's some great ones. Those two that I put from Medium are actually really good as well. But yeah, those are always good things to share. But notice the number of qubits that we're at, even in our advanced system, is in that 2,000-ish range. D-Wave has aspirations of going up to 5,000. University of Tokyo has 20,000, but still, that's nothing when you compare the size of the processors that we have in the classical computing space. So let me pause. That was what I had that I wanted to cover today. Questions, comments, thoughts, feedback. Unfortunately, I don't have the ability to share a microphone. That's the one thing about the live stream approach, is it's really only one speaker, and that's me. Well, we'll keep this conversation going. How can I, as a data scientist, contribute to this domain? That's a good question. And I won't say that I have a complete understanding of the relationship between quantum computing and data scientists. I think where we're at now is that data scientists need the hardware to make some advancements. We need to get to more of that quantum computing, that universal quantum computing, before it's going to really be applicable for machine learning. Now, the only exception I can say to that is the fact that so if you really think about, and I want to go to this slide here for a second to kind of help with this, and this is where I'm not sure I completely have a great answer. But what we're dealing in with quantum computing, or let me take a step back. What we're dealing with in artificial intelligence or machine learning specifically is we're saying we need to train a model. And when we train this model, we are using optimization algorithms. Specifically, we're typically using some type of gradient descent algorithm to optimize our weights as part of developing our algorithm. Now, what I don't know, I probably spelled gradient descent wrong. What I don't know is I don't know exactly how to take this quantum annealing optimization and apply that to gradient descent. As I've done my reading in this, that was the thing. I tried to do a little research to see how those were related, and I couldn't find a good answer. So from a data science perspective, the thing that I think would be very interesting is if there's some way we can use some type of conversion to convert a gradient descent problem into a problem that is solvable by a quantum annealing computer, then we may have something that can help us in this training procedure. I could be wrong, but that was the thing that kind of stuck out to me, is we are doing a form of optimization. We're trying to optimize these weights. I don't know how to do that with a quantum annealing computer. So I don't think that's a great answer, but that's the best answer that I have. But thank you for asking the question. Any advice on resources for those of us who want to start learning more about AI and machine learning? Where I would start looking at AI and machine learning is there are a number of tutorials out there. And what I would do is I would start with a lot of the tutorials. You're absolutely right. The amount of stuff out there can be quite overwhelming. And what I do is I look for tutorials in, do a basic feed forward network or those sorts of things. That's where I find them very good. There are a number of Python books out there that talk about machine learning. But yeah, the number of things, Andrew Ng has some free courses that you can take. We at Award Solutions have some basic webinars and stuff that we do as well. More than happy to talk to you about that if you want to learn any of that stuff. So guys, I want to thank you guys for this experiment. It's been, I think, very good. I'd love to get your feedback. I'm not sure that we're going to use Twitch for our April meetup. Do this one. I'm not sure we're going to use the April Twitch for the April meetup. I wanted to do this kind of quickly when all of this Corona apocalypse stuff happened really in earnest over the last few days. So we wanted to go ahead and try to do this online. And actually, I was very happy about that because a lot of meetups just outright canceled. And so I'm glad that we were able to at least do something. And so we will do this online in April. I don't know what the topic is. I don't even know what the platform is. It'll either be on Twitch again, or it may be using another platform like Zoom. We're going to make that decision over the course of the next couple of weeks, and we'll communicate that with plenty of time so you'll see it. So the next one will definitely be on April 20th. There we go. So it'll definitely be on April 20th. It will definitely be at 11:30. Whether it is on Twitch or not we'll decide. What is the relationship between quantum computing and app development? How will apps be different in the future? It's a great question. And the only answer that I really have is with respect to, it's going to be part of that universal quantum computing. So what is the equivalent of an operating system in a quantum computing space? What is the equivalent of Linux or Windows? What is the equivalent of something like Excel in a quantum space? I don't know. I don't know if quantum is going to become like a math coprocessor, like you see. Intel has a lot of hardware acceleration features built into their chips that do specific functions like encryption. Is quantum going to be something like that? Or is quantum going to be just as kind of its own special case, standalone thing? So yeah, there's a lot of research out there in that. And I don't have great answers. I'm hoping for some great advancements in this space because I think it could be super exciting. I'd love for us to, 2030, we're buying a new laptop and the laptop has, a 7 qubit processor in it or whatever. Yeah, I do agree with you that better cryptography encryption will be based on some of these techniques, but I don't have great examples at this point. All right, guys. Hey, thank you guys so much. I'm going to hang around for a few minutes if anybody does have any additional questions. But other than that, stay safe out there. I know it's kind of scary, some of the stuff that's coming out there. Thank you guys so much for being part of our online meetup, and I'll see you guys next month. And if you have the ability to chat, if you want to put some feedback of what you thought of this, or send it to me directly. If you do have additional things that you want to communicate with me directly, my email address is creece@awardsolutions.com. Feel free to reach out to me there. You can find me on LinkedIn. You can always send me a message, a whisper, as they call it within Twitch. My Twitch name is TechnoChrisR. But until next time, thank you so much.